Worked out.
Yes.
Yes. Yeah.
Don't work it out. Don't
No
say
it.
that.
No it.
No, it.
I worked out yesterday.
Yes. Yes. This is right.
Exactly.
Yes.
So what did I say?
You said worked it out.
No.
Yes.
No.
We all heard that.
Really?
Yeah. Yeah.
Not at once, you said like 3-4 times.
Yes.
Yeah, but I know the difference between them.
Yes. We didn't hear that. Yeah. So is worked out.
Yes, I know the difference between
Good.
them.
All right. Good. Good. Good.
Thank God.
All right. Okay. Next now. Right. Let's record. Yeah, you went to the gym and you worked it out.
He started with
Best place to study. All right.
by sauna.
Kinetic model of gas. KJ, would you like to write the title down?
Yeah. You don't go to gym. You don't play sports or something.
Is maths a sport? Then no.
You just work it out. You
Yes,
don't work out.
that's it. I just work it out. I don't work out. All right, you got this?
You don't have time.
Don't have any time for anything. Now, just remember, we've did this definition already. Pressure is how much something is pushing on something else. As a formula, pressure is force over area. So just remind yourself of that. Force is F, A is area. What are the units for pressure? Pascal. So we say 1 Pascal of pressure is 1 Newton of force over 1 meter squared. Why do I keep writing minus? That should be over an area of 1 meter squared. No minus there. For goodness sake. 1 meter squared, no minus.
Newton meter square.
Yeah, that's, yeah. Okay, just write down the formula at least. Crar.
Yes.
Pressure equals force over area. And I'll have to fix this as well. It's there should be no minus in the power. I'll fix that later. Okay, do you have this? Or what do you need from it? Yeah?
Okay.
Yes? Yeah? Okay. It's the same as, now see the minus should be there, shouldn't it? I put on the wrong thing. Same as 1 Newton per meter squared. The minus should be on that one and not that one.
You finishing?
No, it's okay, you don't need to. We did this already. Okay, can I go on?
Yes.
Yeah. So what we're going to do now, our ideal gas, we're going to think about our gas as being low density. No, listen, Carrera, come on. Our ideal gas is going to be a low density gas of colliding particles with no attraction between them, ignoring gravity. Balls bouncing around in a box, basically. That's what we're doing. No, you don't need to write this down, but the picture I'll explain in a moment. So what we're going to do, we're going to think about our gas like this. So firstly, to make our life easy, instead of having some weird shape for the gas, we'll make the gas into a nice cube. So we'll call this side L, L and L. Okay. Also, to make our life easy, the gas will just be like little balls bouncing around. So they bounce around here, and then they bounce around here, and then sometimes they bounce into each other. Okay. Also, to make our life easy, we're not going to consider gravity. So we're going to ignore gravity
Yes.
in this gas, and we're going to say the density is quite small, so there's not too many of them. So this is the concept that we have. So do you understand what we're doing here? Yeah. So let's have a look at just one of them. So this you do need to write now. So this is the wall, and let's look at one particle. And let's make our life easy and say that it's moving here with a speed of v, and it'll hit the wall and then bounce back and forth. You got that?
Yes.
So we'll say that the time to go from here to here, we'll call the time taken here t, delta t.
But
You need to write this down.
from there to there, no?
From the delta t is the time between collisions,
These.
and v is the speed of the particle.
But I have.
Yep.
But then the time will be, like it's 2.5.
No, I'm just doing this as if it was in motion, but yeah, the t is the time from hitting one wall to hitting the other wall.
What do you mean by time between collisions?
With the walls.
Collisions.
Yeah.
You know the collisions?
Between hitting the wall. Collide means hit the wall.
So the time.
Yeah? Is that okay? So what we're really going to have a look at now is this wall here. Let me enlarge it. So let's imagine there is the wall there, L by L, and what's the distance here? L as well. So the ball is coming in to hit the wall. How fast is it going before it hits the wall? V. And then afterwards it's going V, but it's going the other way, true? What is the impulse? What is the change in momentum? What was the momentum before the collision? mv.
Yeah.
And what's the momentum after the collision? What is it? Come on. Minus mv, because it's going the other way. So therefore, what is the total change in the momentum? 2mv. Tell me when I can continue. I can continue? Yeah. Now, if I divide both sides by delta t, does anybody remember what this left side here is?
Momentum over time.
Change in momentum over change in time?
Energy.
So Rob.
Pressure?
Force. Newton's second law.
I was getting there.
No, you weren't. So, therefore, the force on the wall is 2mv over delta t. Okay. Now, how long between each bounce on this wall here? How much time between the? This keeps hitting this wall, doesn't it? It goes bounce, 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 bounce. How much time between the bouncing? Between what?
Delta T.
Very good. 2 delta t. Okay, 2 delta t. So, unfortunately, you know what? I shouldn't really use delta t here because I don't want to mix it up with that. So just remove the delta from this here in the diagram. Okay, so again, what is the time here? It's 2t. So, where's my pen gone? Come on back. It is 2mv over 2t. That's nice. What cancels here? The 2's. So you get mv over t.
So force is over time over t.
No, because then we can do distance, speed, time. So what's the formula for time?
D1S.
Distance over speed. So what is the distance here? It travelled.
L.
Well, is it?
Do
It's kind of. Oh, sorry. Well, that T is for one movement. So sorry, it is L. So it's L over. What's the speed? V. So this ends up being mv squared over L.
You're proving something.
Yeah, I'm getting to something.
This is getting very confusing.
Yeah. Well, so far, I hope it's okay so far. Yeah. So I want you to write this down. Keep going. Will you stop tweeting? Are you tweeting there? What are you doing? WhatsApping? Safari. Now put it away. Okay, can I continue?
Just,
Right.
Just 5 seconds.
Okay. Now, what is a formula that has force in it that we're doing today? Pressure.
Yeah.
So what's the formula for pressure? F over A. So what I'll do now, I'll take my result I have so far, and I'll divide it by the area on both sides. So what does this become? F over A. Pressure.
Oh,
Pressure is mv squared
it's
over.
mass too.
Huh? Say again?
It's acceleration. Sorry, it's acceleration too.
What? Oh yeah, F is ma. But I'm saying, no. Well, all I'm doing here is dividing both sides by area A. So I divide the left by area and the right by area. Now look, what is the area here? What is the area? L squared. So what is L squared by L?
L cubed.
L cubed. But what's L cubed? The volume.
Yes.
Now, actually I won't write the volume in just yet.
Okay.
Okay. Yes? Can I continue?
Where's the area?
I changed it into L cubed.
L cubed.
Because A is L squared. So L squared by L is L cubed. F divided by A is P. Can I go to the side?
Yes.
Now, our particle is moving back and forth in a straight line. But it's not really doing that. It's not moving in one dimension. It's moving in 3 dimensions, isn't it? So look here. If you had something moving in 1 dimension with V, if it was moving with the same speed in 2 dimensions, would the x and the y part be the same? V and V? No. So what angle would you put here? Well, you don't know what angle it is, but you know, it could be something like 45. So this would be V cos, and this would be V sine. Cos 45 is 1 over root 2. Sine 45 is 1 over root 2. Yeah? Hang
I
on.
don't get the values.
We'll go back a step. Suppose I was saying that this was moving in 1 dimension with speed of 10, then what's its velocity? 10. Now say I was moving in 2 dimension with speed of 10. What's the velocity? Is it 10 and 10 here?
No.
No. It'll be 10
Sine.
cos theta and 10
Sine.
sine theta. Now you don't know what the angle is because the angle keeps changing. But on average it could be something like 45. So for example, sometimes the angles will be 0 if the particle is going to the right. Sometimes the angles will be 90 if it's going straight up. And it'll be somewhere in between. So on average it'll be like 45 degrees. So cos 45 is what? 1 over root 2. So this would be 10 over root 2, and this here would be 10 over root 2. Yeah? My point I'm trying to get to is when you start moving into 3 dimensions, there's an x, there's a y, and there's a z. And in fact, if the speed is v, then on average this one will be v over root 3, this one will be v over root 3, and this one will be v over root 3. I don't want to talk about this too much because it's not too important. All I want to say is that this is when it's in one dimension. Okay, but when it's in 3 dimensions, it's different. When it's in 3 dimensions, it will be v over square root 3 squared over L cubed. That, in other words, to make this problem more accurate, to go to 3 dimensions, this v becomes v over root 3.
So why we don't get rid of the root?
We will in a moment. Okay, I can continue? Yeah. Now, as you said, Karar, we'll get rid of the root, so this will be 1 over 3 mv squared over, now please don't mix it up, this v down below is volume v, not velocity v.
On the up one is velocity.
Velocity. Now, this is the pressure caused by one particle, right? But of course we have many particles. So if you want the total pressure, so I'll just write P1 for one particle, the total pressure, I have to multiply this by all the number of particles. How many particles do I have? How many molecules do I have? You don't know. So I'll just write here n for how many we have. Fair enough? N. Now, what I'll do is I'll bring this v up to the left. So you have P v equals 1/3 n m v squared. Now, what I'll do next, I'll say PV equals 2/3 n a half mv squared. I just put in a 2 and a 2. The reason for doing that is, what does this piece become now? A half mv squared. Kinetic energy.
Yeah.
So now you have PV equals 2/3 n multiplied the kinetic energy of one particle. So if you have the kinetic energy of one particle and you multiply it by all the particles, what will that be? The total kinetic energy. So this is 2/3 total kinetic energy, if you want to write it like that. Total kinetic energy. Now, what is, look here please, the particle is moving around. What is the energy of the particle? It's kinetic energy plus potential energy. And what's potential energy? Kinetic energy plus potential. What's potential? mgh. But remember at the start of the question I said we are going to ignore gravity.
Gravity, yes.
We'll ignore it. So then the total energy is the same as the kinetic energy because we're not considering potential energy. So now we get the result PV equals 2/3 the energy of the gas. Or if you want, you can say it the other way around. The energy of the gas is 3/2 times the pressure of the gas and the volume of the gas.
So final formula is this one.
And this is it.
Given to is only this one?
Yes. Yeah. KJ, I will take the phone off you now and put it away. Listen, I think this is a remarkable formula because it is impossible to know the energy of each individual molecule. However, by knowing the pressure and the volume of the gas, we are able to know the total energy of the gas. what form will this energy be in? Kinetic energy. So I can know how much kinetic energy is stored in the gas by knowing its pressure and its volume. In fact, if I just multiply pressure by volume and then multiply it by 3/2, I have the energy of the gas. Okay? You don't seem too impressed, but whatever.
Because you're like the teacher for me, the only who proves everything.
What's that? You don't like it or you do like it?
No, it's like it's new.
It's new.
Yeah.
Yes.
This thing is new, you know.
They just give us a formula.
Yeah, just give us a formula.
Okay,
This is
No,
that,
but
this
you
is
don't understand. Do you
What was that?
appreciate where it comes from?
Exactly.
Yes. Okay. So what I really think this is interesting is by knowing the pressure and the volume of the gas, which are easy to find, we can know the total energy. So you can write it this way around. You can write PV equals 2/3E if you want. This is the formula we proved. Again, I'm repeating the same thing. So you have the result. Okay, so another formula to get. What happens when you what happens to your pressure as you go deeper underwater? Increases. And as you go up a mountain, the pressure decreases. So there must be some relationship between pressure and height.
Oh.
Okay, so let's try and find that. Okay, so we'll get to that note in a moment. Alright, so this is what we'll do. We'll imagine there's a ball underneath some water. So it's in water here, okay? So here is the ball, and it has radius of r. Okay? So we want to know the pressure. Okay, so what's the formula for pressure? Force over area. Now what's the force pushing on this ball?
The weight.
The weight of what?
Water.
The weight of the water above it is what's pushing down on it. So we have that the pressure is the weight of the water divided by the area. Now let's say that this here is of height h here. We want to know the weight of the water. So what's the formula for weight? That's mg. Yes? But what's the formula for m? If I have density as mass over volume, what's the formula for mass? Density by volume. So we can say that the pressure is the density of water by the volume of the water by g divided by the area. Let's put in the numbers. No, let's not actually. Let's leave it like this, density here. And what's the volume here? Well, what shape is this? What shape is this? A cylinder. Very good. So what's the formula for a cylinder? Pi r squared h. Now what's the formula for the area of the sphere? Do you know it? I don't know if I know it. It's pi r squared. 4 pi r squared
Area of what?
of a sphere.
4/3.
No, that's a volume.
Area?
4 pi r squared.
Pi r cubed.
No, pi r squared.
4 pi r squared.
4 pi r squared. 4 pi r squared. Oh, sorry. Sorry. I don't mean, sorry, this is not a sphere. I said that wrong. It's not a sphere, it's a circle disc.
Oh.
Circle disc. So it's not 4 pi r squared. What is it?
It's
Pi r squared. Okay, what cancels here?
pi r squared.
Sorry.
It's pi r squared.
Wait, hold on. Something's wrong. Volume is pi r squared hg. Area. Hang on, something went screwy here. Oh rats! I've done something wrong. I was supposed to have a h here to cancel these. I don't want a h. Or maybe it was a sphere.
Crystal desert.
Hold on. I'm thinking. What did I do wrong here? Density. Whoa. Area of this is pi r
It just
squared.
changed the color. It was all black.
No, I know it's got messed up. No, it didn't. Sorry, I don't want a H. No, that's. Sorry, it's exactly right. There's no problem with it. The only thing I forgot was to write the G in here. That's all I forgot to write. Okay, what cancels here? The pi's cancel and the r squareds cancel.
Where's G come from?
G was from here.
Oh.
I just forgot to write it. So we have our result. The pressure is equal to the density of the liquid multiplied by G multiplied by H. So look, as the H gets bigger, what happens to the pressure? It increases.
So is the other formula?
So this is the formula.
So what? The pressure?
So this is the pressure as a function of the height. So as the H gets bigger, the pressure gets bigger. So like, I'll do an example, but this is the formula anyway.
As the H gets
Bigger, the pressure increases.
If you are going down, how it gets bigger?
The H is measured from sea level.
So if you are going above sea level, that is minus.
We'll take, we'll take care of that in a moment, but the H is how far deep you are in this liquid or gas from the top of the gas. I know H is for height, but here it's like depth. In other words, it's depth. Yeah. So as the H increases, the pressure increases.
Well, in terms of heights, like going up a mountain.
No, yeah, we measured the depth is from the top of the atmosphere.
Okay.
Yeah.
Just.
Yeah. Yeah. Well, I'm gonna. No, I need to go on because we want to finish soon. You'll have to get it from someone. Can I continue?
Yes.
Yes. I want you to note that often when we measure the pressure of the atmosphere, we use something called an atmosphere of pressure. But all it is if I have 1 atmosphere of pressure, that's the pressure in this room right now from the atmosphere. That's just equal to this 101.35 kilopascals. 101.35. 1 atmosphere of pressure. 1 ATM of pressure is this much pressure. You don't feel it, but there's pressure from the air on you right now.
That's all you're sticking.
Yeah? Just write the definition down. 1 atmosphere of pressure is 101.35 kilopascals of pressure. Okay, continue. Yeah, right. This is at sea level. Okay, so a couple of quick questions. Goodness, come on. What is the pressure if you're 5 meters below sea level? Easy peasy. What's the H here? 5 is the H. Density, 1000, and gravity is the G. So, we multiply them together, and the answer is the pressure on your body is 49 kilopascals. Yes?
Seawater is salty water, so 1030.
Oh yeah, I suppose so.
Yeah.
1030. Yeah. I think though, if this was an exam question, they don't expect you to remember the density of seawater. No, his point is true. So you could use 1000 in the exam. But if you wanted to be more accurate, we could use 1030. No, I wouldn't. So it'd be nearer to 50 kilopascals. Okay, next one.
Next one.
How thick is the Earth's atmosphere?
Very thick.
How can we calculate it?
The radius of
No.
height.
No. So I'll stop you right now. Right. So
we get the V. So
no. Go on. Earth.
I said 7 square.
No, I'm just drawing it. I don't need to know that.
Radius is
It doesn't even have to be a sphere. It would work if it was flat. Earth's atmosphere, kj. Now, you can think about being in the atmosphere as being like underwater. So you could start at the top of the atmosphere where there's no air, and then you decrease a distance of h, like as going under the water. Yeah? Now, pressure equals density, gravity, height. Do you know the pressure on the surface of the Earth?
Yes.
You do. That's 1 atmosphere. How big is that? 101.35 kilo. 10 to the 3. Do you know the density of air?
Yes.
Yeah, I gave it to you last time. It's something like 1.3 kilograms per meter cubed.
It's all even the P is equal to density GH. The answer is K pascal, right?
1.2.
The answer P?
Yeah.
Pressure is, yes, this is the P.
So then why you change it? It's already.
Oh, no, the formula is in pascals. So we have to convert the kilo.
Where do you get the pressure from?
But the last time you said, when you did, you said kilopascals.
Oh, yeah, I just gave the answer as kilopascals. But it's 49,000.
Oh, okay.
Yeah.
1.2.
What was it? 1.2 is the density of air, and G 9.81, and H you can work it out. So you get H is 8.6 kilometers. That's how thick the atmosphere is. That's at least our estimate of how thick it is. We're saying that the air is about 9 kilometers thick. Now, you think about it, that's not too accurate for, well, no, it's actually not too bad.
Where do you get the pressure from?
It's taken as a fact that the pressure on the surface of the Earth is 1 atmosphere of pressure.
You took 1.2 or
1.2 is the density of air. Yeah. If you got the internet there, before we finish, why don't you type in, we can see how good our estimate is, type in the how thick the Earth's atmosphere is or something. What is it?
480
480 kilometers.
480?
Yeah.
Now the problem is, we only care about the atmosphere where there's air that you can breathe. No, you know what? You just type in KJ. How high do you have to go up until you can't breathe? That's kind of what we're looking at.
But most of it's within 10 miles, 16 kilometers.
There you go. Okay. So most of the atmosphere is in 16 kilometers. Yeah. This is, so our answer is not perfect. No, but it's an estimate. It's an estimate. I mean, it's a good estimate because the only knowledge we used was the fact that we are at 1 atmosphere of pressure and the density of air is about 1.2. Now, the reason it's not accurate is because the Earth's gravity is pulling the air closer. It's changing how the air is distributed. In the example of the water in the tank, the water was uniformly spread out. Whereas for the Earth's atmosphere, you know that the air is not spread out. Some parts have lower density and others and so on. But it's an estimate, and it's the right scale. We didn't get an answer like 500 million kilometres. All right, there are the questions to try, and